All right, let's talk about motion, the physics of how things move. And we're going to start with a bit of a paradox. You probably feel like you're sitting perfectly still right now, right? Well, what if I told you you're actually hurtling through space at an insane speed? By the end of this, you'll not only get why that is, but you'll also understand the tools physicists use, things like velocity and acceleration, to make sense of our universe, which it turns out is never, ever standing still.
So let me ask you a really simple question. Right at this very second, are you sitting still? I mean, you'd probably say yes. But you know what? The universe has a very different answer.
And that's because, really, motion is everywhere. It's in the air you're breathing, the blood pumping through your veins, all the way up to entire galaxies just rocketing through space. The big takeaway here is that nothing is ever truly at rest. To really put a number on it, even when you're just sitting in your chair, you're on a planet that's spinning like a top while also orbiting the sun at thousands upon thousands of miles per hour. This gets to a huge idea in physics: all motion is relative. Okay, so if everything is always on the move, how on earth do we even begin to talk about it? How do we describe it with any kind of precision? Well, this is where physics comes in. It gives us a special kind of language, a toolkit for describing this constantly changing world of ours.
So, let's start with the absolute basics, a distinction that people mix up all the time in everyday language, but for a physicist, it's a night and day difference. I'm talking about speed versus velocity. Think about it like this. The speedometer in your car, that's telling you your speed. It's just a number, right? 60 miles per hour, but it has no idea where you're going. That's where velocity comes in. Velocity is the whole package. It's your speed plus your direction. So 60 miles per hour is a speed, but 60 miles per hour north, now that is a velocity.
You know how on a long road trip your speed is all over the place? To get a handle on the whole journey, we use something called average velocity. It's basically the straight line distance from your start point to your end point, divided by how long the whole trip took. It just gives you the big picture. But that big picture, it doesn't tell you how fast you are going at that one exact moment you glanced at the speedometer. For that, we need a way to zoom in, like really, really zoom in. And this is exactly how physicists do it. They take that idea of average velocity and they just shrink the amount of time they're looking at. So they calculate it over 2 seconds, then 1 second, then half a second, then a tenth, and as they get smaller and smaller, look at what happens. That velocity value starts to settle on one single specific number. And that number, the one it's getting closer and closer to, is what we call instantaneous velocity. It's the velocity at one precise moment in time. You can think of it as physics' version of a perfect freeze frame. So we've got velocity down, but what do we call it when your velocity itself changes? When you hit the gas, or slam on the brakes, or just take a turn. Well, that brings us to the next big idea, acceleration. For the early scientists, it wasn't super obvious how to describe this change. Should they measure it against distance or something else? But it was Galileo, with his famous experiments dropping things, who had the big breakthrough. He realized the most useful, consistent way to describe it was as the change in velocity over time.
So that's the key. Acceleration is just the word we use for any change in velocity that happens over some period of time. And remember, it's not just about speed, it's any change to that velocity.
And that means acceleration can happen in 3 different ways. First, you can speed up. That's positive acceleration. Second, you can slow down. We call that negative acceleration or deceleration. Or, and this is the one people forget, you can just change your direction. A race car going around a curve at a perfectly steady speed is still accelerating because its direction and therefore its velocity is constantly changing.
Okay, so we've got all these pieces: position, velocity, acceleration. What's the point of all this? Well, the point is prediction. With these concepts, we can build an incredibly powerful toolkit that lets us predict where something is going to be and how fast it's going to be going.
And it gets even better. When the acceleration is constant, think of an apple falling from a tree, the relationships between all these ideas become surprisingly simple. In fact, they can be boiled down to just 3 elegant and really powerful equations. And here they are, the kinematic equations. Now I know, it looks like a bunch of letters and symbols, but don't get intimidated. All they're doing is connecting the 5 things we've been talking about: how far something goes, how long it takes, its acceleration, and its starting and ending velocities.
And here's the beautiful part. If you know any three of these, you can use one of these equations to solve for the others. It's like having a recipe for predicting an object's future.
And this isn't just a bunch of abstract math, not at all. This toolkit lets us answer some really practical, really important questions about the world all around us. So let's actually put it to work.
Here's the question that could literally save your life. We all know that the faster you drive, the longer it takes to stop. But it's not a one-to-one relationship. Why is it that going from, say, 30 to 60 miles an hour does way more than just double your stopping distance?
The answer is hiding in plain sight, right there in our toolkit. That third equation shows us that the stopping distance is related to the square of your starting speed. That little squared number, that changes everything.
So what does that mean in the real world? It means if you double your speed, you have to square that 2 when you think about stopping distance. And 2 squared is 4. That's right, 4. You don't just double your stopping distance, you quadruple it. This isn't just some abstract math. It's one of the most fundamental rules of road safety, period.
And you can see these physics principles in action right now, in your own home. You can actually measure something as personal as your own reaction time, and all you need is a ruler and a friend.
See, when your friend drops that ruler, it falls with the constant acceleration of gravity. So if you just measure how far it fell before you were able to catch it, you can plug that distance right into one of our kinematic equations and solve for the time. And guess what? That time is your reaction time. It's the physics toolkit right there in your hands.
So let's end where we started, with a simple question. We've seen how physics gives us this amazing, precise language for motion and a toolkit for seeing into the future. But just knowing something isn't the same as truly understanding it. So I'll leave you with this. Now that you really get this v-squared rule, how might that change the way you move through the world?